So Module 32 it focuses on long-term memory, its capacity, and the areas of the brain that are involved in the storage of memories or of information that we've acquired through learning and through our own experiences, and also the concept of external cues retrieval cues, that there are a series of important ones that we need to know for this module that we will discuss in this screencast. From the readings, by now, all of us should know that the capacity of our long-term memory, different from our working or short-term memory, which hold that magical number in our sensory memory, which is fleeting and not very strong. If not brought to working term memory, our long-term memory, its capacity, different from those just previously mentioned, is limitless. This idea that new memories are going to occupy space that is originally where previous memories have been stored, and therefore they're going to be sort of thrown out and we will forget them. This very passive, or I'm going to say library version of the way we store our long-term memories is research indicates that this is not the case. As your textbook explains too, to answer the question, where are long-term memories stored, that there is no specific place in the brain. Instead, that there are many areas of the brain that participate in the formation, in the saving, and in the storage of long-term memory. In fact, your textbook explains very well that the different components of memories, like the memories itself, the different components are distributed across the different areas of the brain. Many of these areas of the brain, logically, were involved in when the event took place. So let's say it's an emotional, let's say a flashbulb memory that is charged with emotion, with stress hormones. Well, most likely, of course, in the memory of that event, these areas that participate, let's say the amygdala, which is the emotional processing area of the brain, or neural network of the limbic system that processes emotions, that will also participate in the memory of that event. It was active during the event, it will participate in the memory of that event, in the storage of that event as well. To answer the question about the role of the frontal lobes in the processing of explicit memories, that would be the first step. Now, we haven't gotten to the areas of the brain yet, but it's important to begin associating these terms, becoming familiar with them. And also, I would suggest, as I will do in class tomorrow, or, well, depending on how you're listening to this, as I suggested in class this morning, when you listen to the screencast, please have this webpage of the areas of the brain so that you can begin, now that, let's apply what we learn, let's try to begin associating this visual of where these different brain areas are located and their functions in the formation and storage of long-term memories. So right now, I hope that you can sort of put this on pause for a minute and locate the frontal lobes in that 3D map online that I suggested this morning. So let's begin associating this area of the brain. So it's a very, very front, the prefrontal cortex of our frontal lobes, meaning the front of the front. The frontal area of these frontal lobes participates in the processing of explicit memories. Please remember that when we're talking about explicit memories, we're also talking about declarative memories, and these are memories that we can consciously recall, that we can consciously declare, meaning explain to others, talk about them. And remember, so when we talk about explicit memories, again, those processed in the prefrontal cortex, in the front of the frontal lobes, and these are consciously recalled. These explicit memories can be either semantic or can also be episodic. I explained this briefly in class. I'll explain them, or repeat this brief explanation. Semantic are facts and general knowledge. Think about traditional things that you learn in the academic setting. Or trivia, and then Episodic are those in which events in which we participated in our lives. Think about episodes of our lives or a certain event in our life in which we were witnesses or we were part of. I thought Myers added this year something pretty interesting. It is that whenever we talk, notice that frontal lobes, we use the plural. For those of you unfamiliar with the brain structure, frontal lobes, we use them as plural because basically there are two of almost every part of the brain, meaning we have a right frontal lobe and we have a left frontal lobe. He makes the distinction in the textbook between these two, meaning that, let's say, in case of an episodic memory, we are going to process more episodic memories that have to do with visuals. If we want to remember where people were in a party or how a certain party was decorated, then we will likely scan through that memory, imagining we were there, and then that will mean that our right frontal lobe will be more active in this type of memory. Whereas if we're thinking about a semantic memory, and we need to know specific information that has to do with anything verbal or anything, with verbal, even with numbers, but that has to do with specific information. The perfect example are passwords. Whenever we try to retrieve a password, then anything that has to do with language will be the left frontal lobe will be more active in the processing of this explicit memory. Before we go more into the brain and its structures and its functions, it's important to begin associating the hippocampus as main player in the processing of long-term memories. And more importantly, also, the hippocampus plays an essential role in the formation of new memories. If, as your textbook explains as well, the hippocampus, if damaged, let's say through an accident or something, or let's say a stroke, if the hippocampus results damage from an event like this, then we would remember our long-term memory will remain intact, but we won't be able to form new memories. What does that mean? Well, that we might meet someone today that we haven't met in the past, and then once that person is out of our visual field, we will immediately forget who that person is or what their name is. Because we can't form new memories. So hippocampus associate that with explicit memories and with the ability to form new memories. These new memories, of course, I forgot to mention, are usually explicit in nature, meaning that we're not talking about classically conditioned associations, or we're not talking about procedural memories. When we form a new memory, assume that it is forming a new explicit one. Because remember that implicit memories are non-declarative. We cannot consciously recall those or declare them, meaning explain them or describe them to other people. Think about when we're writing, we don't need to do that because these days, I guess we're going to have to change the analogy, but Myers and his co-author used this analogy of the save button for hippocampus. And this is for, in the 90s, at the end of the 90s, you needed to, if you did not press save on, let's say, word processing document, if you did not press save, then everything would be erased. And you would lose all the information. Well, I believe that's the sort of, that's why they use this analogy. Not considering that today, basically the default setting is to save basically every certain amount of seconds, so we don't have to go back and press save for us. But the hippocampus, it does, as I was explaining just previously, in the formation. So we meet someone. Oh, your name is XYZ. We save it. And that's the formation of a new memory. We're processing a new memory. If that area, again, were to be damaged, then we wouldn't be able to do that, yet we would remember classically conditioned associations. We would know how to play the piano as a procedural memory-based task, or we would remember explicit memories, but from a long, long time ago. But it is important to understand that the hippocampus does not store these. Perhaps they hold them momentarily, these new memories that we're forming, but ultimately they will migrate to other areas of the brain where consolidation occurs. Now, please understand this. Consolidation is basically are the different processes that happen that are involved in converting a short-term memory or working memory into long-term memory. In other words, when we consolidate a short-term memory, that means that we have formed or we have stored memories in our long-term storage, or we have formed a new long-term memory. Now, also important to understand when we talk about memory consolidation, we need to think about sleep. Sleep is the best memory consolidator. I'm just going to use that term. But in order for dreams to go through consolidation, we need sleep. Even those of you who might think you don't need as much sleep as others do, don't fall in that egocentric trap. And understand that I think, in fact, the book very cleverly, and I was thinking about even doing it myself, the book sort of suggests that you use yourself as an experimental subject and go through 2 weeks of improving your sleep, sleeping at least 1 or 2 more hours every day, and see and try to be observant and try to introspect about whether you observe that you're forgetting things, that you're remembering things, and these instances in which you forget, let's say your keys or your wallet or your bag where things are placed, occur less frequently. And your slide in the text also explains how this, why is sleep essential? Because it is during sleep where the hippocampus goes through, your brain in general goes through the events of your day and they've observed the activity and the rhythm of this brain neural activity that's happening during our sleep, and apparently sort of like in unison or in a choreographed way, the rhythm of the cerebral cortex, where it is believed that long-term memories are held throughout the cortex, and we're talking about not a specific region, sort of a very ample part of our brain, is going to sort of let's say dance at the same rhythm. These neural networks are going to dance at the same rhythm that the hippocampus does. And this is the process through which, many things are occurring here that neurocognitive scientists, meaning those that observe through brain scans the activity of our brain, have sort of located this memory consolidation process, how it unfolds from these scan point of views. This essential role that sleep has to do with memory consolidation only provides further evidence of how efficient the spacing effect can be with our memories. Now, remember that spacing effect is when we distribute whatever we need to learn or memorize or have consolidated in our memories, that information, to spread it out through several days in which there has to be a resting period, that resting period ideally being sleep, and sort of this idea. Well, I should have started with this idea of spacing effect fits perfectly with the essential role that sleep has to play in the storage of memories into long-term memory, in our ability to retrieve them. As this spacing effect is based on leaving a resting period in between our study sessions. So we spread out the information instead of cramming it, instead of mass practicing it the night before. We are dividing it. Let's say we need to, learn 2 pages today, 2 pages the following day, and then in between we have that resting period. Obviously, we are referring to sleep where memory consolidation occurs. Always important to see the relationship between these concepts. So now, we've talked about long-term explicit memories, those that are semantic, and those that are episodic. Now, in your notes, you should find a way to outline. Now we talk about a different type of memories, our implicit memories, those that are also referred to as non-declarative, because we cannot recall them consciously, yet they do have an effect on our behavior and our feelings and our emotions. They make this major division in implicit memories. We're going to talk at least now about only two of them, which are classically conditioned associations, meaning we respond to something in a particular way, but because we associate that stimulus that we think is causing our behavior to change because we've associated it with something that we are not aware of. And then your textbook explains this example about a patient who was conditioned to, I think the doctor placed the tack on the hand, and so the patient would not remember the doctor's name, but would immediately yank their hand, sort of as this reflexive response to this previous experience, that they didn't know why they would yank their hand away. But they could not remember the doctor who their name was. They could not remember any explicit memory-related information about the doctor. So that would be a classically conditioned association, and this is one type of implicit memories that we will be discussing in this unit. The other one is procedural memory, commonly known as muscle memory, and it's basically these skills that are related to motor movement, that we have learned through repetition and practice, and that they are so ingrained that we forget the process through which we go in order to execute these. We just do them. And this is all of you out there, athletes, dancers, any skill that you have developed, even playing instruments, any skill that you have developed, you you just know how to do that and cannot explain. It's because that is a procedural memory, and that other areas of the brain are involved in these two type of implicit memories. Two areas of the brain are primarily in charge of processing implicit memories. The first one of these two is the cerebellum. It's also referred to as little brain. Cerebellum has many functions. It remains to be a mystery, in fact, in many other ways. For neuroscientists today, it becomes sort of this very compelling area of the brain that continues to be explored. For now, I want you to associate cerebellum with anything that has to do with classically conditioned associations. The cerebellum is involved heavily also in motor movement, but we'll talk about that later on in balance. And it's very prone to being impaired by alcohol. So when people drink and they feel that they can't walk in a straight line, it's because their cerebellum has been prone to this. But for now, I want you to primarily associate it with classically conditioned associations. I gave the example in class. Once again, my anxiety when I ride over bridges. Now I've made this association with bridge with another thing that I don't know, yet it is affecting my behavior. So this association, whatever I'm associating driving over a bridge with, that classically conditioned association most likely is stored in my cerebellum, in the very back part of our brains. So if our cerebellum were to be damaged, a person's cerebellum is to be damaged, they cannot develop these classically conditioned associations. They would not know that, let's say, they would not be able to be trained. We can easily associate, it's called associative learning. We are actually wired to do this. But if our cerebellum is damaged, we would not be able to. So if you, let's say, when we learned how to, when we see this, all of a sudden, it's raining outside, and we see all of a sudden this light that we perceive to be, we immediately wait for the impending lightning, and we would not be able to do that association and not prepare for an event, in this case the lightning itself, or thunder, if we weren't able to make that association. This is thanks to our cerebellum. Let's go on with the second area of the brain that is mainly involved in the processing of implicit memories. This is the basal ganglia, also become very familiar with this term. The basal ganglia is one of the older structures of the brain, as the cerebellum is. And your textbook discusses why, these older areas of the brain process implicit memories, whereas newer areas of the brain process explicit memories. So basal ganglia is located in really deep beneath the cerebral cortex. We're talking about the middle, inferior area of the brain. and it's associated with motor movement. But for now, let's associate it with the procedural memories. Now, remember, when we talk about procedural memories, these are implicit memories that have to do with skills that involve motor movement, and they're usually acquired through repetition, and we become so good at them, or we sort of carry them out as effortlessly. But this is because the cerebral cortex sort of works when we don't know how to carry out this movement related a skill. Our cerebral cortex is working overtime, and yet once we become skillful at it, then our basal ganglia becomes sort of the responsible one for executing this, or the main one. And yes, and then we become so good at it, becomes so ingrained that the cerebral cortex, the more conscious areas of our brain, forgets how to. It's as if our cerebral cortex forgets how we carried out, how we learned it, and it becomes an implicit memory. And for the purpose of time, I really recommend highlighting why is it that we do think about that. Your textbook explains sort of these older areas of the brain associated with implicit memories, newer areas of the brain associated with explicit memories, and this concept of infantile amnesia, that we cannot recall events in our life or knowledge we acquired before the age of 3 or 4, and yet the abilities that we learned as infants, like how to walk, right, or how to carry out very basic functions that involve movement, how we remember those, right? Because we execute them today, and we never forgot them. Yet we don't. They're so second nature that we don't recall how to do them. We just do them. So remember that. The role of infantile amnesia and this distinction between the older and newer area of the brains and their relationship with explicit and implicit memories. I'll give you one hint. Has to do with functionalism, or this idea of evolution or evolutionary psychology. Okay, another area of the brain that is involved in the formation of long-term memories and the processing of these and their storage is the amygdala. Now, another very important area of our limbic system. And from now on, when we think about amygdala, I want you to please think about emotions. This is the area of the limbic system, that a subregion of the brain through which we process emotions. And the relationship, if you want to write this down, is very simple. So when we become excited or stressed, we release stress hormones, cortisol being one of them. These stress hormones are going to increase the level of glucose. Glucose is going to fuel brain activity in general overall. At the same time, these stress hormones, let's go back to that step, to the release of stress hormones, is going to signal the amygdala that this is an important event, and this is emotional in nature. And then the amygdala will be sort of initiating this memory, and with this idea behind that, okay, this is emotional, this is you either are very excited, very angry, very scared, so therefore let's try to record this moment, either to prevent it in the future or either to just simply relive it again, but we need to put that mark on it. And this is where the amygdala begins to go in overdrive and begins to communicate with the memory related the memory forming areas of the brain, such as the hippocampus and the areas in the cortical areas, or the cerebral cortex, where the conscious processing of memories. Remember, we want to be conscious of these, and also the implicit areas of the brain are also important, that it can develop these reflexes. Let's say let's say this trauma has to do with something physical, right? I think about veterans coming back from war. They're going to react with any sound, because that sound is signaling perhaps impending danger for their lives. So they need to act very quickly. So again, the elevated level of glucose is going to fuel brain activity in general, and also at the same time is going to work closely with the amygdala, that is going to signal those specific areas of the brain, cerebral cortex, hippocampus, and other areas, informing these explicit and these reflexive responses that we need to be prepared for, in case a similar situation occurs in the future. Now, these emotions that are these memories that are charged with emotions are, I want you to think about flashbulb memories. And these are, as your textbook defines them, these are very clear and sustained memories of significantly emotional episodes in our lives. So whenever we've cried of joy or cried of sadness, most likely we built, because of something that had happened to us, we built that as an emotional memory, therefore a flashbulb memory. And the reason why, now try to again process semantically now that we understand better this term, is to flashbulb associated with something that we can see very clearly. When there are no flashbulbs, we cannot see clearly around us. And flashbulb is because these memories tend to be very vivid. Now, inaccurate too. However, these flashbulb memories, especially the good ones, the ones that in which we were really excited, really enjoying a particular moment, we're going to have a vivid picture of them. However, since these are also types of memories that we tend to retrieve to talk about them, to discuss. Let's say we had, when I get together with my high school friends, we remember things that happened 25, 30 years ago. And in fact, people say, wow, you guys get together and talk about the same events. And well, we just, we like to do that. But the reason why I'm bringing this up is because it's relevant to explain that we've discussed these memories a lot. Flashbulb memories can be vivid and clear to us and be very strong, and however they are prone to distortion, especially because remember, when we retrieve a memory, we're not just pulling out a book from a library shelf. We are basically building it from scratch, and every time we do this, these discussions we're having with other people that are not going to see things exactly as we did, and are not going to remember with the accuracy that other people do. So this information is going to vary, and it's going to be also prone to our emotional moments at the time, how we perceive them in the past. Anyway, this constant discussion, talking about these things with other people and listening to them about the same event, makes flashbulb memories prone to distortion. That's what I've been trying to explain. Bottom line, they're not foolproof. Okay, now just listen loud and clear. Don't become alarmed because it's becoming very biology-esque, I would say. It's important to understand the term of long-term potentiation, but for now, I want you to understand the basics of it. And please feel free to ask me any questions as you may. I'm not an expert, but I'll try to explain as clear as I can. And also, again, this needs to be complemented with the textbook before asking any questions. So long-term potentiation has to do with in this eternal pursuit for where exactly are memories stored. Neuroscientists want to understand the physical component of a memory. Where are memories physically stated or physiologically? Where are these memories in terms of the structures of our brain? And we're going to talk about the study with the aplysia, which is this type of sea slug that is in California. But what I want you to understand between neurons, between nerve cells the nerve cells in our brains, right? There's this space called synapse. And this synapse is where neurons communicate with one to another this is electrochemical communication. In these synapses, when we learn something and when we practice it, which is something I try to explain to my Spanish students, the more practice you do, even if it's just the pronunciation of a word and you do it again. Let's say I'm trying to learn French and I will repeat a particular term in French. Every time I repeat it, I'm strengthening a neural network in my brain, meaning my brain is basically changing. Our brains are physically changing whenever we learn something new, and when we the more we repeat it, the more we rehearse it, the better we store it into long-term memory. That more these neural networks, right, that are nerve cells that are communicating, billions of them communicating with each other, they will become stronger, as if you are lifting weights to build muscle. The more repetitions, the stronger the muscle. will be the same thing happens to these neural networks the more we repeat any action that we're trying to learn or trying to memorize. And so this long-term potentiation, potent, powerful, this is the sort of has to do with these physical changes in these neurons that become more efficient. So when they become stronger, what are we saying? That more synapses begin to occur or begin to space between these many neurons, right? More synapses begin to appear, and therefore the communication, let's say communication between one neuron and another, will not depend only on one synapse, right? Remember, it communicates two neurons between them, but we'll have several other alternative routes. So in a nutshell, we'll talk about it in class as well. But the last thing I'm going to say about long-term potentiation is that it's close relationship with sleep. And think about it. If we just mentioned that sleep is the most, the strongest player in memory consolidation, then it makes sense to understand the relationship between long-term potentiation and sleep too. So both have a positive correlation, meaning the more sleep we have, or the most adequate sleep we have, is going to impact the extent to which our brain is going to go through long-term potentiation to strengthen these neural networks where our memories are thought of to be physically stored, so to speak. Please I forgot to mention one more thing. Please pay close attention to this very short, brief discussion that you have in your textbook about drugs that intend to either improve memory, that are attempting to improve memory, and those that, on the contrary, are trying to make people forget about very bad experiences. Traumatic memories are based on this long-term potentiation principle, right? Process. So drugs that are looking for the erasing of traumatic memories, of course, are going to be drugs that are medication that is going to inhibit the process of long-term potentiation. So that type of relationship, please become aware of it and include it in your notes as well. So that's all for now, guys. Thank you.